almost trivial, but the topics are kind of really, they're really deep and very intriguing. Very cool. So now we're done with special relativity. We move on to quantum physics, which pretty much covers the rest of the semester. I think that relativity probably deserves another week, but quantum is so vast with the number of topics being studied today that we really need to spend a lot of time trying to cover it. It's also really much more applicable than relativity. You know, most of us are not going to spend any time at the speed of light, so it'll never really, relativity will never have a real application in our lives, but many of my students will go into medicine or engineering, and in those fields, quantum mechanics is a much bigger deal. They start off this chapter with this picture of this fly or something. What is this? A black fly, just your standard black fly, imaged by what we call an electron microscope. This is probably a scanning electron microscope image. And you can see the incredible detail, the incredible resolution that you get using an electron microscope. But what is an electron microscope? Simply put, microscopes use waves of light, and they magnify those waves of light so that your eye can see the image at a much higher magnification than normal. They use lenses to do that. They bend the light to do that, bending the light to make the image bigger, and we've seen that with optics. We know how that works. But it turns out that electrons and all massive particles, even human beings and planets and everything else, all are also wave-like. There is a wave associated with them. It's nothing like an electromagnetic wave, except that it's a wave. Okay, that's the only thing that it has in common with the waves of light that we usually use for microscopes. But the waves of matter are much, much smaller, much shorter wavelengths. And that's why they can resolve things at higher resolutions or make images of things that are much smaller. Is because the waves are much smaller. You can think of it as the size of the ruler for measuring something needs to be about the size of the something you're measuring, right? So if you're measuring a pencil on the table, then the ruler that you've got in front of you on the table that's about 1 meter long is sufficient. They're ish about the same size. However, a bad ruler for that pencil on the table would be a ruler the size of an aircraft carrier. Because the aircraft carrier is so much bigger than the pencil that there's not likely to be any markings along the aircraft carrier that are going to be useful to us. And that's kind of the idea when you're using light waves to measure things that are very, very, very small. Light waves are on the order of hundreds of nanometers, which is pretty close to being a micron or a micrometer, 1/1,000,000th of a meter. So anything that is much smaller than 1/1,000,000th of a meter, then the light waves are just not really good at measuring because they're just too big compared to the thing that you're measuring. You want a degree of measurement that's much smaller. If you're measuring something on your skin, a feature on your skin, you want something smaller than millimeters. So you need something smaller than a ruler with millimeter markings. If you're measuring, something much bigger, then you can get away with bigger markings or bigger whatever. But smaller stuff, you need a smaller measuring device. And so the smaller waves that are the waves associated with electrons, which we'll talk about soon enough, are waves that are very good at measuring very, very small things. And this is not even a good example. A fly, you can see a lot of the detail of a fly with a normal microscope. Not this much detail, but a lot of it. a scanning electron microscope can see things even much smaller. This is what the surface of glass looks like under a scanning electron microscope, for example. You know, glass that is just smooth as smooth can be, that's what it looks like under a scanning electron microscope. And there's another type of microscope called a tunneling electron microscope that'll give you even higher resolution. And you can see things like this. You can start to see, I mean, here we have, this is the surface of glass at 100 nanometers, right? 1 micron, 2 microns, you know, that's something, but at 100 nanometers, you're starting to look at you're almost seeing the actual individual crystal formations as this glass takes shape. So you can really get in close with a tunneling electron microscope. With an atomic force microscope, you can even get smaller. But that's a different type of idea, different type of technology and detection. But anyway, so we are going to be taking a look here at, come on, I can't move this thing. There we go. We're going to be looking today at the introduction to quantum physics. What does quantum mean? Does anyone know what quantum means? Or quanta? Anybody take Spanish? It does have to do with things that are really small, but that's actually not what quantum means. In physics, it'd be easy to think it means that because the quantum physics or the quantum theory deals with things that are very small. It only really applies to things that are very, very small. But has anybody taken Spanish or any other Latin-based language?
A little bit of Spanish.
Okay, what does quanta mean?
Like a quantity.
That's right. So you say quanta custa means how much does it cost, right? And it does mean it has to do with it's the root for quantity, of course. And what it really means is, if you really look into the depth of it in Latin, it means something that can be counted, okay? And if it can be counted, that means that there are individuals, okay? Now, why is that then part of a theory here? Well, for the longest time throughout history, scientists and philosophers assumed that matter and space and the universe around us was what we call continuous. In other words, matter was this stuff, kind of like slime or gelatin, that's just made of this continuous flow or this continuous makeup of matter. And you could chop it up into little pieces, and no matter how small you chopped it up, you could always chop it up into smaller pieces. It didn't really matter. There was the one scientist way back, Democritus, 400 BC or AD or whenever he lived, a long time ago, who said that eventually if you started chopping things up, you would eventually get to a smallest piece, and he named that piece the atom. So he actually would be the father of quantum physics, saying that there is this smallest thing that can be counted. But it wasn't until the 20th century, well into the 20th century, in fact, that people started to discover, realize, and put together the ideas that at the smallest scales of matter, everything can be counted individually. That everything breaks down into things that are the smallest piece of what matter and energy and space can be. Okay? And I mean, they broke it down into everything, there's no such thing as continuity, in other words, to them, to quantum physics. In quantum physics, everything is what we call quantized, broken into parts that eventually have a smallest part that can be broken no more. Now, what does this mean? In matter, it means that everything is made up of particles and that there are smallest particles. That makes perfect sense. That's no big deal. We understand that. We accept that. It's been a long time since science has not accepted that. since the early part of the 20th century. The problem is that everything associated with these things is also broken up into little pieces, and there are also smallest pieces to that. That includes energy. We've always assumed energy was continuous. You have so much energy, and you can break it in half. You have so much energy, you can break it into thirds, you can break it into fifths, you can break it in however many pieces you want. Energy is continuous, it doesn't matter. But as you get smaller and smaller and smaller, it turns out we discovered it's not true. When you have large amounts of energy, you don't notice that energy is made up of particles. But when you have small amounts of energy, you start to realize I've got this much energy and it cannot be broken down anymore. It cannot be changed. It only comes in this size, essentially. And in multiples of this size. But it only works when you're looking at very small things at the atomic and subatomic particle level. And it's also true of other things like momentum. Energy is one thing, but momentum we always think of classically. We think momentum just has to do with speed and mass, right? When you get down to particles at the size of the atom, that's not what momentum is. Momentum is defined differently, and it is quantized. It depends on the particle, and it has exact measurable particle amounts that are set in their size, and they can't change. So you can only have this amount of momentum or this amount of momentum, but nothing in between. This amount of energy or this amount of energy, and nothing in between. But then the craziest thing is that it also works with space. At the level of atoms and particles, it works with space. You can be here or you can be here, but you cannot be in between. And you can go from here to here, but you cannot go in between those 2 points. So how do you get from here to here without ever going in between? It's not called anything. Well, you can't. There is a word for it, but we don't use it very often in physics because it has been used too often in Hollywood. So we stopped using it. It's called a quantum leap. We stopped using it because of the show Quantum Leap and the movie Quantum Leap. And the idea that people are always talking about quantum leaps in popular literature and popular science talk. They don't understand it, and the way that they use it is completely wrong. So physicists stopped using the word. But it is called a quantum leap. But it's not really any kind of leap. It's not like they jump from one place to another. They just either are in one place or they are in the other place, and that's all there is to it. And people, once you start talking about quantization, once you start talking about being able to quantify something in those ways, we're not talking about particles that can only be so small anymore. We're talking about space that can only be here or there. That is where people really start to not like this theory. The real problem is that it's not actually a theory. It's not just something that people thought up and said, what if? Maybe this is true. Quantum theory is not quantum theory. Notice that it's not called quantum theory here. It's called quantum physics. In physics, we don't even call it quantum physics. We call it quantum mechanics. It's not a theory. It's observation. Okay? All of this stuff is based on what has been observed. And only on that. There are people who do quantum theory, where they try to push it into the next realm and try to understand what could be from what we do already know. But what we're going to teach here is not quantum theory. It's quantum observation. It's just what has been observed. These things are true, whether or not we accept them, whether or not we understand them. They just are. This is what we have seen, and nothing that we have seen has contradicted this. We have not seen anything but this. Okay? So that's the thing that is the problem. The problem is that people just assume this is just some, weird thinking of physicists, but it isn't. This is observation. And whether or not they believe it, or they understand it, or they want to think it's true, it is true. It doesn't matter. Okay? I start off with that because we are going to encounter again and again ideas that don't make sense, that we have no intuition for, and just are difficult to swallow. But it doesn't really matter. All three of those natural instincts you have to throw out the window, because this is not conjecture. This is observation. Okay? This is not something that we're making up. It's something that has been confirmed again and again and again and again and never been contradicted. It has never been proven wrong. Okay? It's always done by observation of events and experiments. So we'll start off mild here. Well, actually, we're not going to start off all that mild, to tell you the truth. We're going to start off with Planck, who did some experiments. So this is a little bit difficult to understand, but I'll try to explain it in the best way that I can. I'm by no means an expert on these things, although I know a lot more of it than some people do. My expertise is somewhat along the fringes of this, but not really deep into it. We start off with light. Light comes from things that are energized in some way. So the sun, for example, is extremely energized, lots of light coming from it because of all the energy inside of it. It's hot, it's burning, and burning things are always energized and they're always giving off light. And according to the classical theories of energy and light and all the things that we learned from the classical physicists before the 20th century, before Einstein, light should come off of burning things in this continuous spectrum where, as you get hotter and hotter and hotter, the light that comes from the thing that's getting hotter and hotter and hotter should change color towards the blue part of the spectrum, towards the ultraviolet part of the spectrum. It should get, so things that are not very hot usually appear red because they're giving off a lot of infrared and red light. Things that are a little bit hotter, more yellow, right? Our sun is a lot hotter than a campfire, for example. Campfires are orange and reddish, and just a tiny bit of yellow down near the some parts of it. But the sun is yellow and green mostly. It has a much higher frequencies of light coming out of it. It also has a lot of ultraviolet coming out of it, in fact. And then things that are really, really hot lean more and more towards the blues and the ultraviolets. Blue stars are very hot stars, and white stars are very hot stars because white is getting to the ultraviolet. Once you start seeing white light coming from something that's hot, what you're seeing is ultraviolet that is so bright that is overpowering your senses in your eyes. Your eyes can't actually detect ultraviolet, but they can sense it. Okay? So you're being blinded by ultraviolet light at that point. And then it goes off into, higher frequencies still. It gets into X-rays and things like that. As you get much, much hotter. For example, a black hole actually doesn't give off any visible light, and all the visible light gets trapped in it, but on the edges of the black hole, which are still extremely energetic, those edges give off X-rays because they're so energetic. According to classical theory, the more and more energetic you get, you should just keep driving towards that high frequency range, and it should increase in intensity, and there's this point at which it becomes infinite, where you get what we call this ultraviolet catastrophe, where you get so hot that the amount of energy you're releasing becomes pretty much infinite. Well, that's not allowed in physics. The infinities are not allowed in physics because there's no infinite source of energy to supply infinite forces or infinite momentums or infinite anything else. And of course, there's not enough mass to have an infinite mass. There are finite amounts of things in the universe. And once we're out of those things, we can't do anything else. And so anything that comes out infinity in a theory, we try to explain some of the way. We try to describe some of the way and see if we can understand why it wouldn't go to infinity, why it shouldn't go to infinity. And this is one of the things that was done early on by this guy named Max Planck. He has an entire laboratory named after him in Germany now. And Max Planck came up with this idea that energy in oscillators, which is what light comes from oscillating particles, right? That energy in oscillators should be quantized. That it should have, it shouldn't actually be continuous. You know, you just go higher and higher frequency and whatever frequency you want. And this came from it's not just an idea that he just came up with. There were lots of experiments being done at the time that suggested this. Lots of experiments with atoms, lots of experiments with light and stars and other things like this. And this is what he came up with. So an oscillator that has a particular frequency, F, would have this energy, n plus 1/2 times the frequency times a constant. The constant ended up being called Planck's constant. And that if you have a number n, where n is any integer, 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on, that you would have these steps in energy. For the first one, you'd have 1, so 1 plus 1/2 would be 1/2 times h times f. And then for the first one would be 0, so it'd be half times h times f. The second one would be 1, and so on and so forth. And so you get this thing stepping up, and so you have energy levels that exist for oscillators. And this comes from some mathematical theories and also mathematical mechanics or observations concerning oscillators, concerning things that wave or wiggle. And we've already seen this as well. This should look fairly familiar to you. We saw this when we looked at sound oscillations, didn't we? When we looked at the harmonics of sound inside of tubes and things like this. So this is kind of where this is coming from. But what he was talking about was vibrating molecules, vibrating atoms, vibrating electrons, which behave a lot like things that cause sound. So they have very similar mathematics. The big difference was this constant. And this constant came from comparing his theory with the observations, from looking at the mechanics of what was going on in the scientific world. He had to match up what his equation was saying with the actual numbers that they were seeing in the equation, what they were seeing in the experiments, and that required this factor, which is normal. There's always some kind of factor out there. And the factor turns out to be extremely small, 10 to the minus 34. And that is the thing that suggests that this theory, or in this idea, this mechanics, only works for very, very small things. Okay? For very, very small masses, very, very small energies, and very, very small time scales. So very, very small world. The subatomic particle world, in essence. So, his equation in the end ends up looking like this. For a change in energy, if you have a change in energy, then you get, and that's what causes light to be released, by the way, is a change in energy. You get a change. If you have a change in energy, you get this Planck's constant times the frequency of the light that is released. And that gives you quantization of light. That essentially tells you that the energy of a light wave, is quantized by its frequency. You have the Planck's constant times its frequency will tell you how much energy that particular frequency of light can have. The smallest piece of that energy of light. And that immediately threw people over the cliff. They're like, you can't say that light can only come in certain energies. And, well, I think that's kind of a ridiculous statement that you can't say it, because he wasn't just saying it, he was observing it, right? But you can't, I mean, why can't you say it? We say things all the time. We say that light has to be continuous, and there was no evidence that it was. It was just, we assumed it was. We say that, a second is a second is a second, but we say things all the time in science that have no basis to them at all, have no scientific basis in observation or anything else. We say them all the time, so why not say it? Anyway, this experiment done by Max Planck was called this whole idea was called the black body radiation. We refer to it all as black body radiation, but this idea here is one of the first ideas of the quantum mechanics world, is that energy that's coming from objects that give off light is quantized, or in other words, can be counted into little particles, can be separated into these little tiny blocks that are equal to Planck's constant, which is this tiny bitty number, times the frequency of the light. Of course, the frequency of the light is a very big number, but not as big as this one is small. So this ends up being a pretty small number. So here's an example of an infrared frequency at 10 to the 14th hertz. Infrared, 10 to the 14 is a huge number, right? 10 to the 14 is not nearly so small as 10 to the minus 34 is. You know, it's not, well, 10 to the 14 is not nearly so big as 10 to the minus 34 is small. So if you want to measure the energy quanti, the quantum jump in energy between two places that an electron has to go in an atom to create an infrared light, because that's what happens. In the end, when light is created, an electron is jumping from one point to another in energy levels in the atom. So an electron jumps from one point to another in an atom, and it releases some energy in the form of light. What is that energy going to be? Well, the energy is going to be equal to the frequency of the light that's released, in this case, the 10 to the 14 hertz times Planck's constant, 6.63, times 10 to the minus 34, and you get 6.63 times 10 to the minus 20 joules. Now you're probably asking yourself, where is the evidence that electrons do this at all anyway? The evidence was there for the taking. This was not new. Okay, and we'll see this later on here. But you've probably all seen, have you all seen the spectrum of atoms? Where you have a gas of mercury, for example, and then you put that light from a gas of mercury through a prism and split it, and you get individual lines of light. Seen that before? Seen that in a chemistry class maybe? That is the evidence that light coming out of atoms only has certain energy levels that you see, only has certain frequencies. That was the evidence that he was going on. He said, if this is true, then why is it true? Well, oscillators behave this way and light behaves this way. Let's put those two behaviors together and combine them to form this idea, and let's compare it with the evidence. Let's compare it with the facts and see if it matches the results. And it did. And that's what he was doing in the end. It was a lot of work and a lot of different things that he was putting together, but he was able to do this. And it was actually, from our last chapter, it was actually Planck that suggested relativistic momentum in Einstein's theory. It wasn't Einstein that suggested that, because he could look at Einstein's theories and see the mathematical connections, just like he saw the mathematical connections with the atomic spectrums and the black body radiation theory, the black body radiation experiments. He was a brilliant genius at figuring out the math of things. So anyway, Planck's constant. Here's atomic spectra, for example. This is what oxygen looks like when it's being lit up by energy. Remember we said that light comes from things that are being energized. So if you just have oxygen gas in a tube and you energize it, you either heat it up or you put electricity through it or something, it doesn't just give off light in general. It just doesn't give off a mixture of all frequencies. It gives off very specific frequencies. Well, why is that? Because oxygen, down here on our chart, where is oxygen? It's way over there on the right side. It's the one that's kind of bluish on the second row, below helium to the left. It has 8 electrons in it because it has 8 protons in it. 8 electrons means that it's got all kinds of different configurations for those electrons to be in. They can go back and forth and jump up and down all through these different energy levels that it's got available. And this is the spectrum that we see. We don't see light in between these lines here. These lines are the only places where these electrons exist. They jump from here to here and release a light. They jump from here to here and release light. They jump from here, and that's one way to think of it. It's not actually the way to think of it. But anyway, they're jumping back and forth inside of the oxygen atom and going from one energy level to another. And as they go from one energy level to another, they release or absorb light. But they only do it for certain size chunks of energy. That's why we see these certain lights. If it did it for every energy, if it was a continuous thing, if the electron could go anywhere it wanted and not just from one particular energy level to another, you would see a rainbow here, just like you do with white light. If you put white light through a prism, you just see a rainbow. You see every possible frequency. But here we only see certain frequencies. And for a different atom, it's different. You see different frequencies. Every atom has its own quantized frequencies and its own quantized energies that are allowed. So, what does this mean? That's our next question, next thing to learn about. What does this have anything to do with?
Is this the same reason why like the bottom elements are radioactive? Because they set like the spectrum of visible light, they let like.
Good question. It's a really good question, and it was something that was not understood very well, because one of the things that radioactive elements gives off is they give off X-rays or gamma rays, which are light rays. They're just really high energy light rays. And so originally people thought, well, maybe that's an electron that's making this jump, this huge energetic jump. But there's not enough energy in between the energy levels to give that much energy. It turns out it's just not available. And so they thought, well, where did that come from? And we'll learn more about that in our nuclear science section, which we will cover. But what's really happening is that light is not coming from a transition between electrons, but a transition between protons and neutrons inside the nucleus. Inside the nucleus, if you get a shift in protons and neutrons, like they just move around a little bit, which they do every once in a while in big, especially in really big things. In the smaller things, the nuclei are pretty stable. They're not going to move much. They're not going to change much. Move is a bad word to use because we really don't know if they move at all. But we do know that something changes to make them more or less stable. So for example, uranium, which all the stuff that's down at the bottom of the table, that bottom row and the bottom 3 rows, and then a few others on the fourth from the bottom. Every one of those is radioactive. And there are a few more up on the table as well that are radioactive. For example, you have technetium, you have cesium, and so on and so forth. But anyway, the point is that this radioactiveness comes from not transitions in the electrons and releases of energy that way, but transitions somewhere in the nucleus. Some kind of shift or change in the nucleus because it's unstable to begin with and it's trying to stabilize itself and it releases some energy. Now that energy can be light in a very high energy form, usually what we call a gamma ray, but it's like an X-ray. It is an X-ray, there's no difference here. But it can also be in the form of a particle. It can actually release energy in the form of a particle. Because remember that in Einstein's theory, mass and energy are essentially the same thing. And sometimes energy can manifest itself in the form of a particle, like an electron or a positron. Those are two types of radiation that are released by atoms. But also in the form of a much bigger particle, which is called an alpha particle, that can actually kick out some of its protons and neutrons. And that happens also quite a bit. An example of that here is if we have radon here. Radon is a gas that sometimes releases an alpha particle, which is 2 protons and 2 neutrons. And it's so unstable that it just doesn't want those 2 protons and neutrons, so it kicks them out. When it kicks them out, it all of a sudden has lost 2 protons, and it becomes polonium. Right? Polonium will do the same thing. It'll kick out 2 protons and 2 neutrons and become lead. Well, lead is extremely stable. That's why we have so much of it on the Earth. Because everything that decays up here and it becomes right out, eventually decay down and become lead and become stable. Right? So that's why there's not that much uranium on the Earth, and anything above uranium, there is nothing of it on the Earth. It's all been decayed. It's all decayed since it was made by the sun and deposited on the Earth and made on the Earth. But uranium is stable enough to still be around, still be kicking around. But everything else is not stable enough. It's all decayed now. That's the short answer. We'll learn more about it as we go on into our later stuff. So, the next thing we're going to talk about is the photoelectric effect. And the photoelectric effect is an experiment, experiment that was done in the late 18th, early 20th century, late 19th, early 20th century, and it was Einstein who explained what was going on, who was able to actually enlighten the world, enlighten the scientific world as to what is going on. So here's the experiment. Where is the experiment? Here it is. Let's see if we can look it up here. Let's see if it works. Yeah. Okay. So what we've got here is we've got a voltage source, which is going to be a pretty high voltage source, and like a battery or a power supply of some kind. And then inside of this tube that is a vacuum tube, so there's nothing in here, we've got two electrodes each connected to either side of our voltage source. Pretty simple. Outside of this glass tube, didn't mention it was glass, we've got a light source that is going to be variable light source. We can change it to be ultraviolet or any of the visible colors or infrared. So we can change the frequency or the wavelength, but we can also change the intensity up here. And that means how bright it is. So let's put it right here at green, and let's change how bright it is. What we've got right now is we've got 0 volts, but we're going to crank up the voltage just a little bit. So we've got 1 volt. So here's our positive side, here's our negative side, and we're going to turn up the intensity of our light at green. And as we do this, what happens is we get a current. In other words, we get electrons jumping from the negative side to the positive side. As we turn up the light a little bit more, we get a little bit more current. About twice as much intensity, we get twice as much current. We double it again to 80 something, 84, 86 or 88% or whatever. We get more current still, and it's about linear. About linear. You get about twice as much current for about twice as much light, which is what you would expect, because we're figuring intensity is energy, right? We're giving it more energy if we give it brighter light. And that's true. However, there's something else that's interesting. Let's turn our intensity to a nice constant, so we get a nice constant current that's not very big. Now, according to science of the times, the intensity was the thing that determined how much current you would get jumping out of it. Why would we be getting current anyway? Well, because the light is a type of energy. The atoms inside of here are receiving that light, and that energy is energizing some electrons, and the electrons are getting energetic enough to jump out of the atom and then go across to the other side. Okay, that makes perfect sense, I suppose. But according to the science of the day, changing the frequency shouldn't do anything. Did the frequency just do something? It did. It just doubled. We didn't change the intensity at all, but we just doubled the amount of current out. Now it's tripled. Now it's quadrupled. Now, I mean, we're not even changing it by that much. And we're getting a huge change in current. All right? Okay, well, let's go the other direction. That was towards purple. Let's go out here and see what happens. Current to 0. Does it change with intensity? Something weird is happening. I mean, if we increase that intensity, we should get more electrons out. But apparently that's only true for certain frequencies. Okay? So this, and the interesting thing was that it behaved differently for different metals. Right now we've got sodium right here. That's this blue strip of sodium right here. If you change the metal, it changed what frequencies released energy, released electrons. So this started to make people think, what's going on inside the metal that's making frequency a big factor here? Well, that wasn't really the best question. It was a good question, and it yielded some great results, in fact. But maybe the better question is, what's going on with frequency? Light is frequency. Well, again, we go back to our friend Planck. Max Planck says that the energy between two levels is a direct result of frequency, or it's directly related to frequency. So this was already known at the time. But this was not being equated to this experiment. This experiment was not being connected with Planck's discovery from black body radiation. And it was Einstein that made the connection. Einstein came in and said, you know what? If it works for black body radiation, why shouldn't it work for atoms? Why not? And why shouldn't it work for metals with light being shined on it? And he was able to connect the two and show that this predicts what frequencies will give off what energies, what frequencies will release electrons. And he was able to predict what it would do for each type of metal. And they discovered at certain frequencies you get huge ejections of electrons. And then at other frequencies it's just normal. So everyone, you're going along and you're increasing the frequency, and the electrons coming out are increasing, and then at a certain frequency you get this huge peak. And then the next frequency goes down again, but it's still climbing. And so you get these little peaks and those peaks actually coincided with the energies that you saw in the spectrum, the frequencies you saw in the spectrum. So at certain frequencies of light, certain metals like to release their electrons much more easily. And what this led to was the theory that all light comes in these little packets of energy equal to Planck's constant times the frequency of that light. That all light exists this way. It is a natural existence of light. That even though light is a wave, this wave energy comes in these little predetermined envelopes of energy, amounts of energy. And we call these particles photons. So these particles, or these packets, are called photons. They're not a particle in the traditional classical sense. They have no mass. They have no confined space that they live in. No, they're not like something you can pick up and move from one place to another, or you can measure their size. They're not a particle in the traditional classical sense. They are a particle because they have a certain size in energy. They are a certain amount of something. And they are quantized because that amount is set. That amount is not only measurable but calculable. You can calculate it. So, here they give us an equation that the photoelectric effect that was calculated. This is calculated, this is Einstein's calculation, that the kinetic energy of an electron coming out of that metal in the photoelectric effect is equal to h times the frequency minus the, what do they call BE? I don't know what that stands for. Oh, yeah. So they call this the binding energy. Where the binding energy is the amount of energy that the electron needs to stay in the atom, or is holding the electron in the atom. So HF subtract the binding energy, and the weaker the binding energy, of course, the more of these you're going to get out at a particular frequency. And that's what got him the Nobel Prize. So here is an example where we're going to calculate the photon energy, or the energy of one of these particles of light. We have a photon of 420 nanometer violet light, and we want to know, first of all, what is the energy of that light using Planck's equation, and then the maximum kinetic energy of electrons that can be ejected by this light if the binding energy of the electrons for calcium is 2.71 electron volts. So to calculate the energy of this light, you just plug in h times the frequency. We don't have the frequency of the wavelength, so we use the equation frequency equals speed of light divided by wavelength in place of frequency, so we h times speed of light over the wavelength. We plug all the numbers in and we get 4.74 times 10 to the minus 19 joules of energy. That is the photon of 420 nanometer light. The photon for 420 nanometer light is 4.74 times 10 to the minus 19 joules. So much energy is in each particle of that. And you can't break it down to half that energy or 2.5 times that. It has to be integer numbers of that amount of energy for that light. So it has to be 5 times that or 5 gazillion times that, but it can't be 5 gazillion point 2. It has to be an integer number times that. Now, if we're going to convert that to electron volts, remember there's 1 electron volt per 1.6 times 10 to the minus 19 joules. Remember, it has to do with the energy of the charge of an electron. So you divide by 1.6 times 10 to the minus 19 joules to get electron volts, and you get 2.96 electron volts per photon of 420 nanometer light. And then you compare that with the kinetic energy by plugging in that amount of energy and subtracting off the binding energy. So 2.96 electron volts minus 2.71 electron volts, and you get the kinetic energy, which is essentially the leftover energy between the amount of energy of the light you put in and the amount of energy that was required to kick out that electron. And the leftover is the kinetic energy of that electron. Now that's not a very big amount of energy, it seems like. However, for an electron, it's a fair amount. Electrons don't need much to get them moving. So that's the next experiment or discovery made as we move towards quantum mechanics. So, if we now can determine the energy of individual particles of light, we can start to know or understand how to remove these electrons from the atom most efficiently. Okay? So if you have so much binding energy holding in an electron into an atom, 2 electron volts, whatever, then the energy that you put into that, if it's equal to that, will release that electron. If it's more than that, it will release that electron. But the ideal thing is to get it to be just the right amount so that you're releasing the electron the most efficiently without wasting energy. Okay, so here they're showing all the different energies that you have to kind of overcome to get electrons out of an atom. You have rotation energies, vibrational energies, binding energies. Those are for molecules. And then in atoms, you have the energy between the outer shells and electrons, the energy of red light. So these are just kind of roundabout figures. But this is what's required to ionize an atom or a molecule, anywhere from 10 to 1,000 electron volts. And it just kind of depends on the atom. Some atoms are much easier to ionize than others. Ones that are difficult to ionize, dang near impossible, not impossible, but difficult, are the ones that are at the end of that table down there. The ones down here, you have these full valence shells, and so they're very stable, very well bound, difficult to ionize. So, anyway. Once you start messing around with light waves and going up into the higher frequencies, you always end up outside the visual spectrum, outside the UV spectrum, and into the gamma ray spectrum, X-rays and gamma rays. And this was discovered by a guy named Röntgen. Here's his one of his original pictures, I believe. That the one up there is also one of his original pictures. But Röntgen discovered this by accident. He actually was in his laboratory one day going through his drawers, and he had a drawer that had samples of uranium ore. And then in the next drawer over, he had some film, some undeveloped film. So undeveloped film back then, unexposed film, they'd never even taken any pictures with it, was essentially in these little boxes. They were usually wooden boxes, and the wooden box was sealed up so that no light could get inside and expose the film. And the film wasn't necessarily like plastic film like we had when I was a kid, and we don't have anymore today. But it was usually glass or metal that had chemicals on it that when you exposed it to light, it would give you imagery. And so these things were boxed up in these boxes so that no light could get in them. Well, he went in to take some pictures, and he took his pictures with the film, and then when he went to go and look at the pictures, there were these ghostly images in the pictures. And he couldn't figure out what they were. And then he started to realize, these look like the things that are in my drawer. Like the film took a picture of things in his drawer before he ever put it in his camera. And what he finally realized was that the uranium was giving off some kind of light that could go right through drawers, go right through wood. And it would leave an image on his film of the things that were between the uranium and the film. And so he started experimenting with it. He said, well, I'll put stuff between the film and the uranium and see if I can take, some image. So one thing that he did was his hand. And he was able to show his bones in his hand. And then he sprinkled lead pellets on his hand in that picture. In this picture, he obviously put some instruments on here, a compass and some other thing that was made of metal. And he demonstrated that these light rays, these mysterious rays that he called X-rays, because they exposed film like light rays, but they were obviously not light like we see, because they went right through things that normal light can't go through. So we call them X-rays, just, mysterious rays. But he started to realize that they wouldn't go through metals so well. Some metals they would go through better than others. But most metals it just wouldn't go through very well at all. And it went through bone, but didn't go through very well. It would go right through skin, but not perfectly. You can still see some skin and muscle, right? So he started learning a lot of things about these. One of the things that he learned by exposing himself to so much radiation is that you can get sick from it. That you actually start to get degeneration in your skin and other things like this. He got cancer from this. Eventually, it was discovered that you could create these X-rays. You didn't just have to have some radioactive material around that gave off the X-rays naturally. And this was discovered much later on. It was actually Marie Curie, and her husband and her children that eventually did a lot of this research with X-rays and different radioactive elements, and others as well. There were a lot of people that were doing it, but she was the first woman to get a Nobel Prize for doing science, and so we definitely want to mention that. But eventually they discovered that they could make these high energy rays of light, and they eventually did discover that they were light rays, not just some mysterious ray, by having a material that is highly energized. Now remember, we were able to extract electrons out of metal if we shone light on it. Well, they wondered if the opposite would be true. What if we hammered metal with electrons? Could we get light out? And it turns out that if you shoot electrons at very high voltages into metal, you actually can get X-rays out. And that's how X-ray tubes are made. This X-ray tube here is very, very kind of typical X-ray tube. It's usually made of glass, and you have essentially just a light bulb on one end, a filament that gets really, really hot, and as a filament gets really, really hot and starts to light up, it is releasing electrons, boiling electrons off of the metal, essentially. And then you put this end at a low voltage, this end at a high voltage, and the electrons will go from this to this end to this end, from the filament to the other end. The other end, you have a big piece of metal that's cut at an angle, so when the electrons run into it, X-rays come off perpendicular to that surface, and they come out of the tube sideways like this. And the type of X-rays that you want, the higher energy X-rays require different metals than lower energy X-rays. Most tubes are just made with a tungsten target, and they're used usually to go through skin and muscle. And that's the kind of X-ray tube that they use at the dentist, that they use at the hospital for the most part. Most X-rays are that way. Some X-ray tubes are different for special reasons. For example, the X-ray tube in a CAT scan machine, I believe they have more than one actually in a CAT scan machine, is designed to give different levels of penetration with different energies of X-rays, and so that they can map out things in 3 dimensions. If you're doing soft tissue X-rays, for example, for a mammogram, they use a different X-ray tube. I think they use copper or silver for that one because you don't need as high. You don't want a really high energy X-ray. That's if you're just looking at soft tissue, because it'll just go right through it and you won't see anything. You want to lower that energy of that X-ray and not go through quite so well, so that you can see tumors and things like that. Very important for mammograms. So, how do we calculate the energy? Well, again, it comes down to our friend Planck. This equation, E equals h times I. It's the frequency of the light that tells you the energy of the light. And so in this case, they're telling us that we have 50 kilovolts difference in a cathode ray tube, which is what the X-ray tube is up over. So if there's a 50 kilovolt difference between the ends, that's going to be the energy that the electrons are going to hit with, and we want to use that as our electron volt energy, essentially. So we get 50 times 10 to the 3, 50 times 10 to the 3 volts times the conversion to electron volts times the conversion to electron volts is here, and then we're actually going to use let's see, H here is, if we can actually use H in a different form instead of 6.6 times 10 to the minus 34. This is used with electron volts, so you use 1.6 times 10 to the minus 19. It's just a different version of H for different units. And then you plug it all together, and you get 50 kilo electron volts for the energy of the electrons. For the energy of the photons. Now this is the beauty of using electron volts for your energy when you're doing radiation. If you know the voltage or the potential difference that the electrons are going through, in this case 50 kilovolts, then the light that's going to come out is going to have an energy of 50 kilo electron volts. We just did all this calculation, we got the same number. And that's the beauty of it. And this is what they use when you're doing radiation physics and stuff like this. They use electron volts for this reason. They use electron volts for this reason because the energy of the electrons creating the radiation is essentially equal to the energy that the photons are going to have coming out in kilo electron volts. You just instead of doing a bunch of calculations, you just say, oh, 50 kilo electron volts. Makes it simple. Anyway, what really happens though is kind of interesting. It's the same. It's a very similar thing that happens with the photoelectric effect. You get this radiation that comes out, but every once in a while you get this spike in energy, in intensity. Not energy, but energy and intensity. At certain frequencies, this is the frequency, and this is the actual intensity. As you go up in frequency, you get more and more intensity to a point. At some point, it drops off. But there are some places where you get these spikes, and those spikes happen where there are specific transitions within the atom. specific electron transitions within the atom where it kicks out extra energy at that place. We call this down here the Bremsstrahlung, which means breaking radiation in German. So this is the energy that is required to stop all those electrons that are boring into that metal. But these places right here are what we call the characteristic X-rays. So each metal has different characteristic X-rays and a different range for their breaking radiation. These characteristic X-rays are the things that can really be useful because they're so intense. Let's see here. The ultraviolet. Here they're going to talk a little bit about ultraviolet radiation because it's also dangerous like X-ray radiation because it can ionize things very easily, which means it can take things apart. That's what you don't want radiation to do. You don't want radiation to start taking things apart in your body because it damages things. It can damage molecules, it can damage proteins, and then your body can make mistakes trying to repair those proteins. So anyway, here they want us to calculate the energy of a photon and estimate how many molecules it could break apart. So the energy of the photon is just h times f or h times c over lambda. We end up calculating that using the wavelengths they've given us, and it turns out to be 12.4 electron volts of energy for that. Well, how many can that break apart? Probably just one. Let's say here. 12.4 electron volts. Let's go back to the table here. Electron volt can, oh, here we go. So you can actually do one molecule with 1 electron volt, and we've got 12, so we could do about a dozen molecules with just one photon. So that could be dangerous. And you can actually see it doing this. You can see it breaking down things in paper and ink. Paper and ink are mostly organic molecules. And organic molecules can easily be broken down. They're not very strongly bound together. Organic molecules are very weakly bound together. So pretty easy to break apart. Now let's see what the implications of these little tiny particles are. How many photons per second come out of a light bulb? Well, we need to know, first of all, what is the kind of the average photon for visible light. Visible light, see, 580 nanometers. Average wavelength of 580 nanometers. So if we use 580 nanometers as our wavelength, we get our energy per photon, about 3.43 times 10 to the minus 19 joules. Now, for a, what bulb are we doing here? 100 watt light bulb. A 100 watt light bulb is giving off, do they do that calculation? Oh yeah, right here. They say 10% of our 100 watt light bulb is actually giving off energy. So 10% of 100 watts is 10 joules per second. So the photons per second is going to be the energy per second times divided by the energy per photon. 10 joules per second, 10 joules per photon, or sorry, 3.4 times 10 to the minus 19 joules per photon. And you divide those two and you get 2.92 times 10 to the 19 photons per second. That's a lot of photons, right? That's why we don't live in the quantum world. There's so many of these little quanta, so many of these little particles of energy coming out that we can't perceive it as particles. We perceive it as continuous because they're coming out so many so fast. That's why we don't really have any real intuition for quantum physics, because it doesn't exist in our world. Our macrocosmic world is not quantized according to our perception. So, all right. Let's see what this one's all about. So color vision. We have these photons that come out and we see red. Photons come out and we see green. The reason that this is really interesting, put on filters, right? They're actually doing this for a couple of different reasons. But the reason that this is really interesting is because our eyeballs are actually designed to see things quantum. Inside of our eyes and our retina, we have two types of these things in our retina. Let's see if we can see them both here. Here's a nice image of the retina. Kind of hard to see them in that one. Easier in this one. So this one, they've actually color-coded them for us. So here we have our rods and cones, right? The rods are these cells or these structures, I don't know what to call them really, but the rods are these long structures that are designed really just to measure the intensity of light. And what those rods do is every time a photon of any kind of light comes in that is energetic in the right energy spectrum for this rod to capture or to feel, what these rods do is they essentially absorb those photons, they absorb that energy. So anytime one of those things comes in and hits one of those rods or passes one of those rods, it detects it and sends a little signal to our brain saying light, intensity, right? But those things are not very good at knowing how much energy just hit them. They just count the number. They don't know how much energy each one of those things has, each one of those photons has. The cones down below are literally cones, and they are actually designed to detect what frequency of light has come through. In other words, to measure the amount of energy of each photon that comes in. So these things are quantum mechanical structures in our eyes. The rods just measure bright and dark, and they're really bad at measuring the actual energy. The cones don't measure light and dark, they just measure the individual energies of each of the photons. Together, they can be used to do great things. Together, they can give us incredible resolution. We can see details, and we can see movement and everything else. Separately, they don't do so well. Okay? Without the rods, our cones are almost useless. Without the cones, our rods can only tell us light and dark. You know, if you ever go out at night on a very dark night, where you can't really see any color, you can only just see black and white, and you'll notice that everything is super fuzzy. You have almost no clarity of vision. Everything is super fuzzy, and that's because you're using your cones alone to see. Right? When it's super bright outside, you have a very similar problem. You can't resolve things. Things aren't only fuzzy when it's super bright out, they're complete. There's like no definition at all. You can just see blobs, you know, and that's because your cones have very little resolution without the rods. Working together, they work great. But if you're using only one or the other, if you've overloaded one or underwhelmed the other, you don't have good vision at all. Very quantum mechanical thing. All right, let's see. We're on section 29.4, photon momentum. All right, we'll go ahead and hit this at the end. Cover the next stuff next time here. Okay, so now we know that photons are a particle of light or a package of light energy, and that every frequency of light has its own size of package of energy, its own size photon, and that these photons are not only, it's not only easy, it's not only fairly simple to show that light has these properties because of the way it releases certain energies of things and doesn't release certain energies of things, whatever else, but it is also part of our life. It's part of our vision, for example. But we can take it even one more step, and I talked about this. Did I talk about? No, that was my other class. Did we talk about Halley's Comet?
The tail forming of the sun.
Yeah, just last week? Or was it a long time? Okay, so it was you guys, okay. So anyway, this is photon momentum, right? So if light carries momentum and you have that solar wind we were talking about, then of course photons carry momentum as well, and that pops out in the science. It comes out in the theories and it comes out in the actual observations as well. Here they're not showing Halley's Comet, they're showing Hale-Bopp Comet, and that's fine. But momentum is carried by photons and can transfer from photons into mass. And this is an illustration of what would happen. You have a photon that's coming into a particular piece of matter, like an electron, and it scatters off of that electron. That's what we call a collision between a photon and matter, photon and electron in this case. It scatters off of it. What happens is that it loses, or it transfers some of its momentum to the electron, and then it bounces. You can think of it bouncing off. We call this scattering. And it afterwards has a different energy with a different frequency. So it's a different photon. So it changes what it is. It changes its nature by transferring this momentum. After this collision or scattering, the electron gains some momentum. In other words, it moves, right? This is called the Compton effect. So, the momentum in a photon is rather small. Let's calculate it. A visible photon has a wavelength of 500 nanometers, and photon momentum is measured by, they do give it to us right here. Here we go. It is, again, Planck's constant divided by wavelength. So it's really quite a small number. So our Planck's constant, 6.63 times 10 to the minus 34 joules per second, joules seconds, divided by the 500 nanometer wavelength gives us 1.33 times 10 to the minus 27 kilogram meters per second. Very, very, very small. Now, how does it change the energy of the electron? Right? If we have this 1.33 times 10 to the minus 27. Well, if that is the case, we know that momentum for an electron is equal to mass times velocity. We change that to be velocity equals momentum over mass. So this is the momentum it receives from the photon divided by the mass of the electron. And it actually kicks it off at 1,460 meters per second. That's pretty fast in our world. In the electrons world, that's not all that fast. Electrons are moving faster than that all the time. Kinetic energy for the electron. If you multiply it out just using the mass and the speed in meters per second, then you get 9.64 times 10 to the minus 25 joules. If you convert that to electron volts, you see it's actually quite a small electron volt number. 10 to the minus 6 electron volts, micro electron volts. Whereas electron volts for electrons can go really high. The photon energy, however, is 2.48 electron volts, quite a bit more. Lot bit more. So only a small amount of that energy was transferred into the electron. However, if you have enough of them, you can do cool things. And this is something that has been the speculation of scientists and engineers for many, many years. And that is the sailing spaceship. And instead of a wind sail, you have a big light sail, a big mirror that you deploy into space. And we do have materials to do that with. We've had them for a long time. Mylar is a metallized plastic. It's a plastic that is reflective, and Mylar balloons are made of it. And we've made many balloons. We've made huge hot air balloons out of Mylar, the ones that have circumnavigated the globe, for example. But now it is time to deploy a spaceship with a solar sail that is just hundreds of meters across. Um, so I don't know when the next one is. The first one failed because it failed at takeoff, but I don't know when the next one is. But you can see this picture in this picture here. These 5 people or 4 people standing next to this sail here. This thing is huge. Okay, it is a monstrous beast. And eventually, you could. The idea of this is that you would have a rocket that flies off into space and shoots some spaceship off into space in some direction, as getting it going as fast as it can, away from the sun. And then you deploy this sail after that. And then you have this source of propulsion that just keeps going and keeps accelerating you and keeps accelerating. It doesn't accelerate you extremely quickly, but it does accelerate you more and more and more and more, as long as you're pointed away from the sun. And eventually you're going so fast that, I mean, after you get past Saturn or Uranus or something like that, you're going so fast that you just disconnect from the sail and you end up winging out of the solar system at a super high speed. So it's a pretty cool idea. It has been used in many different science fiction movies as well. However, once you get going so fast, you're eventually going to get relativistic. This is a possibility for momentum transfer with particles. If you have photon momentum transfer with very small particles, it's very possible you could get an electron going close to the speed of light. And once you do, you have to start being relativistic, of course. And what does relativistic mean? That means that the gamma factor is going to come into play eventually, right? So let's see. Where do they show that? Yeah, they don't really show the use of the relativistic formula for that, but that's okay. Here they're just here's the example. They're showing. They want us to show that momentum is equal to the total electron over c for the photon. In the previous example, it's fine. It works out. But anyway, it can get relativistic in a quick hurry. No pun intended. Next time, we will talk about wave-particle duality, which is another one of the huge controversial and also grossly misunderstood parts about quantum mechanics. And we will have a homework set up for you here in a little bit. So, have a good day. We will see you later. Yeah, let me get my recording started here. Stopped here.